Everyone, in this video we're going to be solving a non-standard equation. We have 8 to the power x equals 32x, and we're going to be solving for x values. I'm going to manipulate this equation a little bit, and then we're going to use a special type of function. I'm also going to talk about the graph, and I'll show you some stuff. Okay, let's get started. Now, when you have an equation with x and some base number to the power x, you can kind of put those two things on the same side and then kind of clean it up a little bit to make it appropriate for our special function. So let's go ahead and do that. I'm going to go ahead and multiply both sides by 8 to the power negative x, or in other words, divide by this. That's going to give us 32x divided by 8 to the power x equals 1. And of course, I only want the x and 8 to the x on the same side. I don't want the 32. Let's go ahead and divide both sides by 32. And that's going to give us x over 8 to the x equals 1 over 32. Awesome. This is almost the form that I want it to be. But 8 to the x is in the denominator. So we can write it with a negative exponent, so that x and 8 to the power something are multiplied, and that's equal to a constant. So this is the type of thing that I want. Obviously, I want to turn it into something nicer, such as x times e to the x or t times e to the t, so I can use my special function. Okay? And we're going to see visually what that function looks like. So I'm going to be using natural log here in order to change the base. You know, with logs we have a change of base, but it also works with exponents. So we're going to go ahead and write the 8 as e to the power ln 8. That's going to be x times e to the power ln 8 to the power negative x equals 1 over 32. And then these two exponents obviously are going to be multiplied, giving us x times e to the power negative x ln 8 equals 1 over 32. So far we haven't changed anything except for the 8 to the power negative x. Now we're going to go ahead and try to get something that looks like this. T e to the t. So if this is my t, can this be my t again? No. This is supposed to be the t, so we kind of have to change the x. And that's pretty easy because I have x and I need negative x ln 8, which means multiply both sides by negative ln 8, which is a negative quantity by the way. So it's going to give you negative x ln 8 times e to the power negative x ln 8 equals negative ln 8 divided by 32, because we multiply 1 over 32 by negative ln 8. We did it on both sides, so we're good. Just to tell you, or just to give you an idea what this number looks like, this is about negative 0.065. Now why is that value important? You'll see in a little bit. I'm going to compare it to another number and you'll see what I mean by that, okay? But here's what we're going to do. We're going to work the right hand side, because I got my t to the t here, but I didn't get something like that on the right hand side. So we kind of need to make it that way too. So instead of writing this over and over, let's just go ahead and work on the right hand side only. First, I'm going to multiply the top and the bottom by 2. And you might be questioning, like, why are you doing it? Because if you think about it, 2 as a power, 8 to the second power is 64. So I want to get something like that. But it's going to be a little different than this one, because we have a negative 2, not a positive 2. See what I'm saying? Okay. So this is going to be written as negative 2 ln 8 times 1 over 64. And notice that 1 over 64 is a fraction. In other words, it's 1 over 8 squared, right? So I can kind of write it as 1 over 8 squared. And that can also be written as 8 to the power negative 2. And that is important because that's actually going to be something that I'd like to use. But how? Again, we're going to use a natural log identity. Remember, we wrote 8 equals e to the power ln 8. So we're going to use that again. Let's use it. 8 can be replaced with e to the power ln 8 and multiply that by negative 2. And you're going to get e to the power negative 2 ln 8. I just skipped that step. I hope you don't mind. I just multiply the exponents. And now I do have a multiplication symbol here, right? Now, this is good because notice that the number here and the exponent here are the same. That was my goal. Now, let's go ahead and write the left-hand side. Instead of, we avoided writing it because that would, be too long. Now we can write it because we want to compare the left-hand side and the right-hand side. So, here's what this looks like. When you compare the two sides, you do notice, hopefully, that x equals 2 actually works, right? Now, what is that special function? The special function is Lambert's W function. So if you apply Lambert's W function on t e to the t, it just gives you t. So this is kind of like my t, and this is the t, the same t. So it's kind of like t times e to the t. And that's going to give us, when we Lambert both sides, we're supposed to get negative x ln 8 from the left-hand side and negative 2 ln 8 on the right-hand side. And when the ln 8 cancels out, we end up with x equals 2. But here's the million-dollar question. Is that the only solution? Ta-da! We got to be careful. And the answer is no. Let me tell you why that's not the only solution, and that has to do with some special function we talked about. So here's what happens. First of all, let's take a look at the graph. Notice that the graphs of 8 to the x and 32x intersect at 2 points. So there should be 2 solutions. We only found one of them, which was x equals 2. And obviously that works, right? You could have guessed it at the very beginning, because 8 to the second power equals 64, which is 32 times 2. That's how I kind of thought about this problem, right? It's easy to make these problems up. But the other solution is a very, very small number. And if you plug it in, it should also work. But what is that number like, right? So let's go ahead and take a look at some solutions. Real solutions. This is Lambert's W function. And as you can see, there are 2 branches here because of the value of our x. And here's going to be the real solutions. 2 is exact, even though it kind of says approximately. But the other solution is going to be about 0.0335. Okay. Now, why do we get 2 solutions? And that can be explained by Lambert's W function. Let me go ahead and copy what I found earlier. I said that negative ln 8 over 32, which was equal to my negative x ln 8 blah blah. So this was kind of like my t e to the t value, which in this case happens to be my x value. You could also call that y, I guess. So I guess that would make more sense. Let's go ahead and set it equal to y e to the y. And that happens to be my x, right? Because I had to do the inverse function here. Hopefully you see what I did. This is the graph of Lambert's W function. But notice that there's a cutoff point, and our x value here actually is about negative 0.065, and that just happens to be greater than negative 1 over e. Why is negative 1 over e important? Because that's where our function makes an interesting turn. And if your x value is between negative 1 over e and 0, any vertical line that you draw is going to intersect our function at 2 points, which means there's going to be 2 solutions on that interval. But if your x value is greater than 0 or less than negative 1 over e, then you should be fine. Well, actually, you don't even have a definition for less than that. But anyways, let's just say you have something greater than 0 like this, then you're going to have a single intersection point. That's why we do have 2 solutions. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.